Have you ever just stopped and wondered what the actual building blocks of life look like? And I don't mean those static, boring drawings you see in a textbook. I mean in real, living motion. Well, welcome to this explainer. Today, we are taking an awe-inspiring tour right into the hidden nanoscale world. We're essentially going on a safari to observe exactly how the fundamental building blocks of life, and really, the materials of our entire future, are assembled. Okay, let's dive right into the agenda for today. First up, we'll cover the limits of sight, followed by breaking the diffraction barrier. Then we'll get into visualizing biological building blocks, move along to hybrids and synthetic polymers, and finally, we'll wrap up by exploring the future of nanovision.
Section 1. The limits of sight, hitting the wall.
To really appreciate where we're going, we first have to understand the ultimate scientific roadblock we've faced for centuries. Simply put, we cannot build, manipulate, or truly understand what we physically cannot see. For decades, traditional light microscopy was our best tool, right? But it came with a hard physical limit caused by the diffraction of light. Basically, when looking at incredibly tiny things, everything just devolved into this blurry, static blob. We literally had to kill samples, freeze them, or completely dry them out just to get a decent look using electron microscopes. But now, enter super-resolution microscopy, or SRM. Think of this as our new set of superglasses. SRM completely bypasses that physical light barrier, allowing us to capture sharp, dynamic subdiffraction imaging in living, operating systems.
So what are we actually looking at through these new superglasses? We're looking at molecular assembly. You can think of this like an incredibly advanced, self-building Lego set. Individual molecules just naturally organize themselves, without the superglue of rigid chemical bonds, to form intricate, functional structures. From the very membranes of your own cells to cutting-edge synthetic materials, molecular assembly is quite literally how the magic happens.
Section 2. Breaking the diffraction barrier are superglasses.
So how do we actually bypass the physical limits of light? Well, there isn't just one magic lens. It's more like a whole toolkit of techniques. Let's break down the big three without getting bogged down in all the heavy technical specs. First up, we have SIM, which uses a really clever structured grid of light to create interference patterns. That brings our resolution down to about 120 nanometers. Then we have STED. STED uses a special laser to essentially turn off the glow around the edges of our target, which shrinks the visible spot down to between 25 and 80 nanometers. And finally, we have SMLM, Single Molecule Localization Microscopy. Honestly, this is the real game changer. It works by making individual glowing molecules literally blink on and off over time, which lets us pinpoint their exact locations down to an incredible 20 nanometers.
But the truly crucial point here is just how far we can push this technology. Under optimal conditions, SMLM can push resolution down to an astonishing 5 nanometers. Just to put that into perspective for a second, a single strand of human DNA is about 2.5 nanometers wide. We are tracking individual glowing molecules at a scale that scientists considered absolutely physically impossible just a few decades ago.
Section 3. Visualizing biological building blocks, the living Lego.
With these tools, we aren't just taking really good high-resolution photos anymore. We're essentially shooting living movies. The absolute key word here is dynamic. We can now watch incredibly complex phenomena unfold in real time. We can see tiny fat bubbles, called liposomes, migrating through a cell and actually stretching out into moving tubes. We can watch peptide fibers actively swapping out their building blocks to reach equilibrium. We've even observed artificial protein threads growing continuously in one direction, almost like they're alive. And, it's not just complex cellular biology. We can even see exactly how casein and whey proteins interact to create the very texture of the yogurt and cheese we eat every day.
Let's look at how this builds into practical applications, like nanomedicine. Because DNA is programmable, scientists can actually fold it into specific shapes. They call it DNA origami, to use as tiny delivery vehicles for drugs. Using these super-resolution techniques, researchers watch this happen step by step inside actual living cells. First, the programmed DNA tubes enter the cell. Next, they dynamically bump into and interact with lysosomes, which are basically the cell's recycling centers. And finally, the researchers could actually watch the DNA origami get captured and degraded over time. Seeing this precise interaction is absolutely vital for designing drug carriers that actually reach their intended targets.
Section 4. Hybrids and synthetic polymers, the synthetic safari.
Nature is, without a doubt, a master builder. This is especially true when it combines organic proteins with hard inorganic minerals, a process called biomineralization. By using SSM, we can watch how gelatin behaves inside growing calcium carbonate crystals. This gives us the literal blueprint for how nature builds hard tissues like seashells, bones, and teeth. Furthermore, Think about what happens when we inject synthetic nanoparticles into the bloodstream for medicine. Proteins immediately swarm them, forming what's called a protein corona. SSM allows us to measure exactly how deep these proteins penetrate the particles. Understanding this is absolutely critical because that protein shell completely dictates how the human body reacts to the nanomedicine.
And this right here is where super-resolution microscopy completely overturns old scientific assumptions. Let's look at synthetic supramolecular polymers. For the longest time, scientists just assumed that in certain water-soluble polymer fibers, the individual molecules only swapped places at the very ends of the fiber. It made sense, right? But by using a specific SRM technique called two-color storm imaging, researchers could watch the exchange in real time. The discovery? Turns out the exchange happens uniformly across the entire backbone of the fiber. Being able to directly observe these mechanisms instead of just guessing is entirely changing the way chemists design new synthetic materials.
Section 5. The future of nanovision beyond the horizon.
If you take away just one crucial thing from this explainer today, let it be this. Super-resolution microscopy has shifted our understanding from static, dead snapshots to dynamic, living movies. By finally being able to see the real-time assembly of these molecular components, we don't have to guess how materials form anymore. We can actually observe the mechanisms as they happen. This fundamentally changes rational material design. It means we can intentionally engineer vastly superior targeted nanomedicines, smarter responsive plastics, and highly sustainable new materials for the future.
There's a line from the research that I absolutely love, and it perfectly captures the ultimate promise of this technology. By combining imaging with tools that actually manipulate the molecules while we watch them, it's allowing biological researchers to not only see the previously invisible, but to also touch the previously inaccessible. Sight leads to interaction, and interaction leads to unprecedented innovation.
We've completely shattered the limits of light. We've tracked the movement of single molecules. We've watched artificial DNA interact with living cells, and we've seen the blueprints of bone and synthetic fibers rewritten right before our eyes. So I leave you with this thought to ponder. Now that we finally have the superglasses to truly see the invisible building blocks of our world, what will we build next? Thank you so much for joining me on this explainer. Keep wondering and keep looking closer.